Hi, my name is Drew. I'm presenting a paper that I wrote with Anthony Steed, and we're both from University College London in the UK. We were looking at how good people are at perceiving where volumetrically captured avatars are looking when they're consuming this type of media in a head-mounted display. So first of all, I want to talk a little bit about what I mean by a volumetrically captured avatar. So volumetric capture is filmed content that in some way allows 6 degrees of freedom movement. And there's a bunch of different ways that you can achieve this. Specifically here, we're looking at a free viewpoint video technique. So in this kind of technique, you have a central character performance like you can see here. There's a lot of different cameras around the outside facing inwards which capture that performance. And then there's image processing and 3D processing that turns this into animated, textured 3D mesh. So specifically, our content was filmed with Dimension Studio, who are a commercial studio in London. Our avatar you can see on the left, this is what he looks like textured up, and then on the right you can see the geometry. So why do we think that these are interesting? Why do we think that we need to look at eye gaze in this context? So volumetric capture is increasingly being used for producing virtual reality content. So here you can see a screenshot of a piece of content that came out last year that was a tie-in with Blade Runner. It's called Memory Lab. And the character on the left is volumetrically captured and then inserted into the scene. This type of content production has some nice features. So one of them is that you don't need to do any pre or post-hoc 3D modeling because it's being captured from a real-world performance. So in some ways, it's quite similar to a film production pipeline. And also, because of that, you get some quite nice characteristics. It's quite realistic in some ways. For example, you get quite nice cloth dynamics. But this type of filming also has some problems. One of the main ones being that at the moment, these experiences aren't fixed at the point that they're recorded. And this has an issue in terms of eye lines. So quite often these pieces of content are filmed, each character is filmed separately, and then they're assembled into a scene at the end. And this means that all the eye lines need to be worked out in advance. The actor needs to be standing in the right place. They're looking at these targets which are affixed to the wall. And because the takes are quite long, because there's limitations on cutting in VR, getting all these things right on set is actually quite challenging. So it's really important that we understand what kind of tolerance we've got, like how good are people at knowing where the users are, where the avatars are looking, and how precise do we need to be on set. Okay. So there's a lot of related work in eye gaze assessment. Almost all of it is based on 3 seminal papers from the 1960s. So Gibson and Pick in '63 did an assessment of dyadic gaze. So that's how good we are at assessing that somebody is looking at us, so mutual gaze between 2 people. Klein in '67 extended this to talk about triadic gaze. So that's how good we are at assessing that somebody's looking at an object of mutual attention. I also wanted to mention, there's a lot of research and I can't go over it, but I also wanted to mention this paper from 2013 by Roberts et al. Because it's the one that's probably most similar to ours. And they also looked at virtuality humans, which is similar to volumetric captured avatars, but they were looking specifically at dyadic gaze, so mutual gaze, whereas we look at triadic gaze here. Okay, so to look at this, we performed a user study. The task was very simple. So there's a volumetrically captured avatar in front of you here. And somewhere between you and him is this yellow floating pipe in space. The users had to rotate the avatar until they felt he was looking at the pipe. So they had a hand controller, they push on one button to rotate him one way, and the other way, another button to turn him the other way. So they're only rotating him in one axis. When they think he's looking at the target, they pull the trigger, and then we change a bunch of parameters, which I'll talk about in a second, and they do it again, and they just do it on repeat. So I want to mention that we presented all of our stimuli statically. So although we had recorded video of our actor fixating the targets, we only took a single frame of that, and that's what we presented to the user. Okay, so the protocol was repeated measures. We had 36 participants with an even spread of male and female and a mean age of 29.4. Okay, so what did we vary? What were our independent variables? So the first one was the display resolution. So we used 2 displays. We used the Vive and the Vive Pro. And the hypothesis here was that a better resolution display would lead to improved task performance because the users would have a better view of the eye. We also varied the location of the target with respect to the avatar. So here you can see a top-down view of what the task looked like. There's our avatar, and that's where the targets were in relation to him at 15-degree intervals. And all the targets are 1 meter away from the point between the avatar's eyes. And we also varied the avatar angle, so where the avatar was looking. So we had 7 3D models that we presented, with the avatar looking at 15-degree increments. So we had 2 head-mounted displays, 9 target angles, and 7 avatar angles. And users gave an answer for every possible combination, so that's 126 data points per user. Okay, and what metrics did we look at? So the first one was accuracy, how good were they at the task? And we measured this using the mean of the absolute error angle. So we're only taking the magnitude of the angle and taking the mean of this. And we also looked at the common error. So this is the amount that if you include the sign when you're taking the mean, where's the middle? And naively, you'd expect that the common error would always be 0. If the answers were normally distributed over the right answer, then you would get a 0 result here. But frequently in the literature, we find common errors which are not 0, indicating that participants tend to over or underestimate gaze in some direction based on some factor. So the classic example of this is that Klein found that people tended to overestimate eye gaze judgments in the direction of the head turn. So the head turn draws the eye gaze further in the direction of the head turn. Okay, so I'm not going to go over all the results. I'll just do the ones that I think are most interesting, the rest are in the paper, and I'll do discussion as I go as well. Okay, so we didn't find a difference in task performance between the 2 HMD resolutions. And this was unexpected because it seems pretty likely that an improved view of the eye would lead to better task performance. But it's important to remember that we only performed it with a certain set of parameters. So the user and the avatar were always 2 meters apart, and we've only tested 2 HMD resolutions. So it's possible that if you varied these things a bit more and you had more variety, then you would get a result here. Okay, in terms of accuracy, so how good people are at assessing eye gaze, we found that it is significantly different for different target angles. So users are much better assessing eye gaze for targets which are close to them. So on this graph here, the green and blue bars are between the regular and the pro HMD, and you can see that they're really very similar for each level. And the one in the middle, so a lower bar is a better task performance. And the one in the middle is for the target, which is right between you and the avatar. And then as they diverge further away, you see this fairly symmetric decrease in task performance. And this has an interesting implication for creating volumetric content, in that you can probably sacrifice accuracy of eye gaze for objects which are further away in order to ensure that it's more accurate nearby the user. So for example, you could subtly rotate the avatar a little bit to get the eye gaze to be correct close to the user. Okay, and also we found a common error based on the location of the target angle. And specifically, users tended to draw the mean value towards themselves. So for targets which are further away, the user is perceiving it as being closer, or they're drawing it closer. And this isn't seen in real world studies. So we weren't expecting this. But it's probably caused by VR displays' known issue that they cause underperception of distances. So there's 2 things happening. One, you're assessing the eye gaze of the avatar, but you also have to assess where the target is in space and try and direct the avatar's gaze in that way. So this is probably what's caused this. Okay, so in terms of limitations and future work, all 3D reconstructions, the 3D reconstruction that we've used has limitations. The model reconstructions are not perfect. And this is a limitation of the technology currently. So there's artifacts potentially in the textures and in the shape of the eyes. We've made our 3D models available. They're in the supplementary materials. So if anyone wants to repeat the experiment, then they're there. And if you just want to have a look at the models and see what kind of artifacts we're talking about, they're available. Also, we only looked at triadic gaze. So in all of our cases, we're talking about this target, which is somewhere in the world that we're getting the avatar to point at. And so we haven't looked at mutual gaze. And obviously, this is a really important social cue, so that's going to be really important going forwards. We've also only looked at horizontal gaze assessment, so what degree horizontally were they able to assess. And vertical gaze assessment is going to be really important in VR, particularly because people are different heights. So when you go into a VR experience, your height isn't fixed. So it's possible that where the avatar was looking when it was recorded is not your height. So we need to know what kind of tolerance we've got here as well vertically. And also, we've only recorded one avatar. So we don't know for sure that our results are going to generalize to different eye shapes and different face shapes. Okay, so in conclusion, we did a user study with 36 participants. We didn't find a difference between the two head-mounted display resolutions that we checked, but again, we only checked two at a set distance. We found that accuracy is much worse for targets which are further away. And also we found a common error shifted towards the user, which is different from face-to-face scenarios. Okay, thanks very much. I will.
Andrew, thanks for the talk. I noticed in your captures, the actor only had their head in a neutral pose in the neutral gaze position.
Yes. Right? Yeah.
And so the non-neutral vector was always combined eye and head rotation. Yeah. So I guess two questions. Was there an actual eye rotation relative to each head rotation? What was that? And could that have had an influence on the HMD resolution, because participants may have been judging by head direction over eye direction? Yeah,
yeah. So there is basically, we just asked the actor to act naturally, look at this target in the way that you naturally would. So there is rotation. It's partially head rotation and it's partially eye rotation. And ideally, it would be better to control for that. So you'd have, you'd have head rotation at varying degrees, and then also eye rotation at varying degrees, and you'd do the test for all those things. And the second question was, will it have an impact? And the answer is probably. So if users are not being able to see the eye properly, then they're probably guessing based on the head rotation. And the amount of space that the eye is taking up in the head-mounted display at that distance isn't a lot. So yeah, definitely.
Okay.